transportation without energy is just nothing. So how much energy it's consuming, we can see from it. And the demand of the energy worldwide is more on those developing countries. And for that matter, especially in the transportation sector, that energy will be more dependent on the petroleum-based or hydrocarbon fuels. And you know, with hydrocarbon, what is the consequence? So when we burn hydrocarbon, the limitation we have is because the carbon ratio in the mix is too much, then there will be huge generation of carbon dioxide. So the global CO2 emission from transportation sector is one of the highest. As you can see from this figure, it stands at the second. And unfortunately, while the amount of CO2 production from the energy sector with some of the sectors is decreasing, but with the transportation, still it is increasing at accelerated level. So here you can see from this figure again, the transportation sector stands with just second in the generation of CO2 emission. And out of this again, the road transport is taking around 74.5%. So based on this prediction, by 2050, the transportation sector will emit around 12 gigaton of CO2 equivalent per year, which is from the current, which is 8 gigaton of CO2 per year. So these are the main challenges which the world is trying to address in many ways. So what we have observed with the unfortunate occurrence of this COVID-19, in fact, it was a blessing for the energy, especially for the emission. So because of, it was like a rally for the world. So there was a decline in the production of CO2. And of course, there was less activity, and as a result, we had less consumption of energy, and subsequently, we have less production of CO2. Unfortunately, immediately the recovery started, the production of CO2 also picked up. Even though there was a discussion by the world leaders that the recovery should have to proceed in a sustainable way, but many countries preferred to continue the same old way. So many of them, they have dropped the intention and they have started exactly the same carbon-based path. So as a result, by 2021, the energy-related CO2 emission grew by 6%. So just my topic today is more towards the mitigation aspect, and as hydrogen as part of the mitigation process. So many ways we can mitigate the CO2 emission from the transportation. One way is energy intensity reduction, just minimizing the amount of energy we consume. Well, with the current trend, that may contribute little, but it cannot be the only solution. But if we try to reduce the carbon intensity of the energy source, then that can contribute a lot while generating more energy or by utilizing more energy, but still less effect on the environment. So these are what, if we proceed in the current momentum, we follow the green. If we proceed with the zero net emission, then we follow the blue. And if we accelerate, it may be difficult to reach the zero emission, but if we try to accelerate, then we may pick up with the orange color. So our options at today's case is like following the accelerated way. So there are different sources of energy which can be categorized as zero emission technologies, and there are lots of advantages and disadvantages associated to them. So our current practices are mainly focused on the biofuels, with the synthesis fuels, the bio-based fuels, or the alternative fuels. Their impact is not as such because we have wide range of limitations with them. Like, for example, if you consider biodiesel, even though it has a huge potential, but we cannot utilize fully into our current engines. So the only way we can use is by blending it with that of the carbon-based fuel. The same is true with bioethanol and bioalcohols. And with the others, like the hydrogen energy as a combustion engine fuel, or hydrogen energy as a fuel cell fuel, or the battery electricity. So I will not go into the details of what are the advantages and disadvantages, but what we can say here is, we can notice that the hydrogen energy source can beat with regard to its advantage as compared to that of the battery electric. Then the limitations with the battery electric, what we have is, one thing, it has higher cost. The other thing is it has lower capacity, especially with the energy density. It has 400 megajoule per meter cubed in comparative to 34,600 megajoule per meter cubed of gasoline. So this is one of the biggest barriers, in addition to those mentioned in the previous slide. And as you can see from the market aspect as well, because we have not much alternatives on the market, still the market for electric vehicles is growing, but the growth doesn't take into consideration the huge demand available for the vehicle market. So as you can see, the current state of the market, in 2021, around 16.5 million cars were on the world road. And in fact, this is an increase to that of in 2018 by 3 times. And in 2022, in the Q1 market, there about 2.2 million cars have been sold from electric vehicles. In fact, half of the market is available in China. So since the transportation sector's demand on energy as well as on the vehicle is huge, we cannot substantiate with the electricity vehicle only. So we need to think about hydrogen fuel cell as well as hydrogen combustion chamber. So with the hydrogen fuel cell, as you can see, what we have, the storage of the energy is done by hydrogen fuel itself. So the battery we require in here is only for the regeneration of the energy from the braking. And as a result, the energy density will increase definitely, because as compared to that of a battery, the hydrogen energy has higher energy density. So the delay period will be less. So as you can see over here, this is the main cell which converts that of the chemical energy of the hydrogen into the electrical energy required to drive the car. So its efficiency Of course, it has more efficiency as compared to the conventional internal combustion engine, and there is no emission at all. The challenge with this, still the technology is recent, so there is more to be done, especially to expand the market. As far as the hydrogen internal combustion engine is concerned, the setup is similar. The only thing, the fuel cell is replaced with the existing internal combustion engine. So hydrogen being utilized as a fuel with existing internal combustion engines. More preferably spark ignition engine, but there are also efforts to utilize this hydrogen energy in compression ignition engine. And there are also works undergoing to utilize hydrogen energy in the aviation industry. So what are the features of hydrogen? Well, the features of hydrogen, so the attractive point here we have is the energy content and the wide range of flammability limits, the auto ignition temperature, higher auto ignition temperature, and higher octane number, which are more convenient for improving the efficiency of combustion chamber. Yeah. The other thing is about the burning speed, which has higher laminar flame speed, and also the laminar flame temperature is high. So these effects because of this effect, the combustion efficiency can be improved, but we have some challenge with, especially with higher laminar flame speed. Controlling of the combustion process is a big challenge. That's why there was huge concern in the past. Hydrogen energy in the combustion chamber is not a recent scenario. It has been there in the research and development for over 200 years. So we have 4 stages or 4 phases in the hydrogen usage for internal combustion engine. The early 19th century, then early 20th century, then the 1970s of fuel crisis, and the current. The current one is motivated by the decarbonization drive. And of course, hydrogen has become a center of focus as a result of for long-term storage of energy. So the challenge in the past were the production of hydrogen by itself was based from carbon-based fuels. So because of the production of hydrogen, up to 830 million tons of CO2 used to be produced. So hydrogen was not a solution in the past because it was being produced from carbon-based fuels. The other challenge is cheap prices with the other renewables as well as with the carbon-based fuels. And loose policies and regulations. It was not favorable for the use of hydrogen as a fuel. Cost of hydrogen production by itself in the old days, it was quite expensive. And that's why even in many cases, people used to prefer to use syngas instead of hydrogen. And storage of hydrogen was also a challenge. Nowadays, because of the innovations, this issue has been slightly solved. And combustion related, as I mentioned in my previous slide, the combustion control is one of the concerns. But despite these all concerns, it was being professed by many researchers that hydrogen would be the sole non-petroleum based commercial fuel in the future. This was stated by Prof. Das in 1990s in one of his papers in hydrogen energy. So what has been changed in recent years?
Excuse me, Prof. Fitri, I think we have 5 minutes left. Thank you.
All right. Okay, I will try to conclude. So we have some driving factors or driving forces which have led us to change our status quo. Among these, which are some of the list here you can find. So because of this challenge, many countries are shifting towards renewables. And the decarbonization has been the motto for the world now. Net zero emissions have been proposed by 2050. And share of renewables is increasing globally. And when we are designing renewables, again, because of their intermittent nature, we need to design with like higher than their capacity, because we need to look at the base load. So as a result, there will be surplus of electricity when they are generating at their peak. And as a result, we require long-term storage. And now hydrogen has started to serve as a long-term storage. So these are the factors which are now changing. And another factor is that of the geopolitics. So there are different ways of producing hydrogen, but our focus here is that of the green hydrogen. That is the only solution for the reduction of CO2 emissions. And that is the only way of sustainable utilization of hydrogen. Otherwise, our main interest here is to utilize the surplus production of electricity from renewables to produce hydrogen as a storage mechanism. By then, hydrogen will be utilized as a source of fuel for the transportation sector. So green hydrogen production is by the use of electricity from renewables for the electrolysis process. So the green hydrogen production, I will not say more about this. It is quite the same thing what I said before. So it will be utilizing the renewable energies for the generation of the hydrogen by electrolysis process. There are advancements in the electrolysis process, and the cost of production is reducing. And beside that, there is also a mature technology on the combustion technology of using hydrogen. So combine this, green hydrogen can serve as a means for the supply of energy to the transportation sector. So that's why many of the original equipment manufacturers are gearing up to the utilization of hydrogen for the automotive sector. So these are some of the screenshots from different OEMs. They are facilitating the use of hydrogen in their car engines. And however, we have some existing challenges still. Yeah, I will not go to the list, but the most important thing is still we shouldn't be focused on the positive side of the hydrogen. Still, hydrogen has higher global warming potential, which is 11 times that of CO2. So we need to look at from the avoiding leakage of hydrogen. Otherwise, it will be a source of global warming as well. So as a conclusion, hydrogen internal combustion engines can serve us as a short-term energy solution for the transportation sector. Hydrogen fuel cell electric vehicles, they will play a big role in the long term. Hydrogen energy market should have to be supported with infrastructure expansion as well as improving the current policy and regulation. But the most important thing is addressing the global warming issue related to hydrogen, which we need to control leakage in the upstream as well as in the downstream. So by that, hopefully, hydrogen will serve in the sustainable development. Now, let me get back to you. Yeah, the other, maybe I just forget one more important thing. You know, we are requesting the original equipment manufacturers to give us different solutions while we are demanding them to give us electric vehicles. Then on the other side, we are asking them to give us fuel cells and internal combustion engine vehicles, then different technologies of internal combustion engine vehicles. So when the demand is diversified, the OEMs are also being stretched over. And as a result, they are failing in everything. So this is also another challenge. So the world should have to be consistent with one form of energy source for the driving of our vehicles. So by having said that, then now let me get back to you the question which I raised it previously. So does my presentation address the question? Still not. I'm not here to give just answer, because if I give answer, it is like a promotion. So just the question will give or will motivate to think and to look after this, then it will be like our communal effect to address the issue and to participate in the process. So by that, I have finished my presentation. Thank you all. I really appreciate. Thank you.
Thank you, Professor Fitri, for a wonderful presentation and a wonderful thinking point you have presented us about the future of energy. I think we have one or two questions from the audience. Is there anyone who want to ask question? Yeah, please. Please mention your name.
Yes. Thank you very much, Dr. Fitri, for the presentations. I have one question about the future of mobility based on the green energy. How about the economical sides of these projects? Like, I can only imagine the electric car is quite expensive, so not everyone can afford it. How about your research? Thank you. Oh, my name is Raihan. Thank you.
Yeah, you can answer directly.
All right. Okay. Thank you very much. So this is a very good question, and yes, the economic aspect should have to be also taken into consideration. As I have mentioned in my presentation, the motivating factors of this hydrogen as a sustainability is because of the economic aspect as well. Because one thing, the production of hydrogen, the cost of production of hydrogen is declining. The other thing is the production of hydrogen is not purely for the generation of hydrogen only. In this case, we are using hydrogen as a means of storage for the surplus of production of electricity. So here we are just killing two birds by just one stone. So that will help us to decrease the cost of energy in the automotive sector further. So that's the aspect we have here. I hope I have addressed it.
Yeah, thank you. Yeah, is that okay, Ms. Raihan? Okay, I think because of the time, I think we have to conclude this session. Let's give a big applause to Professor Fitri Thank you very much for your participation in this conference, and we are looking forward to your next participation in the future. Thank you, Mr. Fitri. We would like to thank you and then give this session back to the organizers. Thank you.
All right. Thank you very much, Prof. Yeah.
All right. Thank you once again to Professor Dr. Fitwi Y. Hegos from Sultan Qaboos University, Oman, and also our moderator, Dr. Insinyur Zahrul Fuadi, STMSC, IPM from Universitas Syah Kuala, Indonesia. Now, ladies and gentlemen, we will continue with the keynote speech. This time, it will be delivered by Dr. Terence Esomba from National Central University, Taiwan. And the keynote speech will be moderated by Dr. Irwansyah STMN from Universitas Syah Kuala, Indonesia. Dr. Terence will join us via Zoom, while Dr. Irwansyah will be moderating from the venue. We would like to invite here at the stage, Dr. Irwansyah.
Thank you, Ms. Rayhan, as the organizer. Actually, we already going to the last session for the keynote speaker today. So before we go through the speak from the Professor Terence, let me introduce first. Our keynote speakers is Professor Terence Esomba. He graduated from University of Orleans, France in 2012. And then for master degree, he continued also in the University of Poitiers in Department of Mechanical Engineering in 2009. And for the undergraduate, he studied in Department of Space System Engineering in Institute of Polytechnic de Sciences Avancées, France in 2008. For the professional experience, he already started for the lecturing in 2012 to 2013 in Department of Mechanical Engineering Institute of Technology of Orleans in France in 2013 to 2015 as the postdoctoral in Medical Augmented Reality Research Center in Chang Kung Memorial Hospital in Taiwan. And in 2015 to 2020 as the assistant professor in Department of Mechanical Engineering, National Central University, Taiwan. And right now, he's also served as the associate professor in Department of Mechanical Engineering, National Central University in Taiwan. Good afternoon, Professor. Long time not to see you. I think it's more than 4 years after graduated. I could not just send email and message to you right now. Thank you so much for your time. You already spent a lot of the experience want to share in our conference today. So the current research that Professor Terence already worked in terms of the mechanical design of medical robots in optimal mechanism in synthesis, mechatronic design of medical device, instrumentation of medical tools, and data measurement experience. So the Professor Terence is more work in terms of the mechanical design of medical robot as well as the others in the instrument system, also in the medical field. So he is also one of the our professor in National Central University in Taiwan, he teach us, especially for me. He is one of the my supervisor when I study there. So I'm not to do the time. Let me see and then hear attentionally for the speaks that we presented by Professor Terence Stem for you. Please.
Hello, can you hear me?
Yes, we can hear.
Hello, thank you, Dr. Irwansa, for this nice presentation. So forgive me, I'm not very familiar with Zoom, so let me share my screen. Okay, I think you should be able to see it. No?
Presentation, but it's not full. Please
Okay.
push the button
okay.
for the
Now
full
it should
screen.
be
Yes.
full.
Yeah, right. It is already.
Okay.
Okay, please.
Okay, so again, thank you, Dr. Irwansa Idram, for this nice presentation. So my name is Terence Esomba from National Central University in Taiwan. And the objective of this presentation today is to introduce you the contribution of mechanism science, mechanism design for the design of medical robots. So in this presentation, I will first briefly introduce the situation in Taiwan on medical robots. And then I'm going to illustrate two examples, two medical applications that I personally address with medical robots. So the first application will be echography on incubated newborn. And the second application will be bone reduction surgery, which is a topic that I actually collaborated with Professor Irwansa Idram. So let's start with the situation and motivation in Taiwan. So Taiwan is considered to have a very advanced healthcare system. It's ranked 9th in International Healthcare Index, and it's also among the top 10 country in medical tourism destination, meaning many people actually come to Taiwan for medical treatment. So it is a very advanced healthcare system. And if we switch the focus in medical robotic, Taiwan actually massively use medical robots compared to the size of its population. There is a large number of robots compared to the population of Taiwan, which is roughly about 23 million Taiwanese people. So if we consider just the most famous robots, medical robots in the world, which is Da Vinci, since between 2004, when that robot was introduced in Taiwan, and 2021, that robot only has performed more than 50,000 surgery. So more than 50,000 surgery in Taiwan during this period was performed exclusively by Da Vinci. And by 2017, that robot performed more than about 60% of all surgery, all considered surgery. So at the end, it shows that people in Taiwan are very acceptant with medical robot technology. One of the things to mention is that the majority of surgery performed by medical robots are not refunded by health insurance. And yet people are still willing to take surgery because they seem to be aware that using medical robots bring more safety and more effectiveness. So to conclude, Taiwan massively uses medical robots compared to its population. Now, if we focus on locally developed medical robots, Taiwan has only 3 companies that design medical robots. One is Highwind Technology, one is Brain Navi Technology, and a very recent one just this year has proposed a new robotic system for orthopedic surgery. And as you can see on the dates, it is very recent. Those companies are very new. So although Taiwan massively uses medical robots, locally developed medical robots are very few. There are very few medical robots locally developed. So there is a great potential to develop medical robot locally because the population is already very accepting to medical robot technology. And for the story, on the picture you see here, that gentleman is actually the CEO of the Brain Navi technology. And on that picture, he actually volunteered to be the first one to test the nasal swab collection robot for the COVID pandemic on him personally. So he volunteered to test the robot. And during an interview, he mentioned that although he fully trusts his engineer and his technology, he admitted that he was quite scared that the robot may harm him during the process. And he allegedly asked his engineer to work on this aspect to make the robot feels less impressive to the patient, and also to make it seems safer. To my opinion, one way not to make it look safer, but to make it actually safer, is to work on the mechanical design aspect, on the mechanism of the robot. By working on the mechanism of the robot, you can actually make it safer. You can improve the kinematic, meaning the quality of the motion, and you can also reduce the cost. The robot they use for this application, for example, is a 6 degrees of freedom robot, meaning the robot has 6 joints. To collect a nasal swab, you don't need so many you don't need so many degrees of mobility. So you can reduce, if you address specifically the kinematic and propose a mechanism that performs this kinematic very specifically, you can actually reduce the size of the robot, the weight of the robot, and the cost of the robot. So to illustrate that, I'm going to present 2 medical applications I have worked on. The first application is a mechanism that we imagine for the intracranial echography on incubated newborn. The situation is that when some babies are born prematurely, they are extremely fragile to infection and to physical contact. So they must be placed in incubator for a while. And you cannot take them out of the incubator unless there is an emergency. They have to stay inside the incubator. And during this period, very regularly, the doctor has to perform intracranial echography to monitor the development of the brain during the early stage of the postnatal development. So they have to go through this kind of access panel and to insert this very small ultrasound probe and place it on the fontanelle of the baby. The fontanelle is the soft zone you have on the skull where, because you have soft tissue, the ultrasonic wave can still go through. So basically, he has to drag the echograph and go from one baby to another. And that procedure is very repetitive and also very uncomfortable, because you can visualize that he has to enter his arm in the incubator and he has to manipulate the ultrasound probe. And of course, he has to be very careful, because in the room, you have about 20 to 30 incubator, and all the babies are sleeping. And if one of them wake up, then all the baby will wake up. So this is very delicate process. Our idea is to, because it's a very repetitive and uncomfortable process that he has to do several times a day and on several babies, our idea is to propose a teleechography robot with a mechanical arm that will go inside the incubator to perform the examination. And the doctor can remain in his office, and using an ultrasound remote control and a communication system, he can remotely control the robot. And the robot will be manipulated by a medical assistant from one baby to another. So here our focus will be on how to design this mechanical arm. So to begin with, because before proposing a specific mechanism, we need to study the motion that the doctor has to do to perform the examination. if we know more about the kinematic, we know what kind of mechanism can generate that kinematic. So we went to the hospital with our equipment, with our motion capture equipment, an optronic system. We place a motion tracker on the ultrasound probe, and we ask the doctor to simulate an examination. It's quite easy to simulate because he always has to take the same image cuts on the brain, and then he will analyze the image later. So that's why it's very repetitive, because he always take a few cuts image, he saves the image, and then he goes observe the image on his office. So it's very fast and very repetitive. And we were not allowed to go on real baby because they were afraid to wake them up. So we use a doll instead of the baby. So then by analyzing the data we collected, we came to the conclusion that the motion is quite particular. We have two remote center of motion, meaning there is two center of rotation. One center of rotation that is located at the access panel. Basically, the arm has to go inside and has to rotate around this point to avoid any collision. And once inside, then there is another center of rotation that the ultrasound probe has to turn to rotate around inside the incubator. So the proximal remote center of motion is basically to place linearly the tip of the ultrasound probe, and the distal remote center of motion is to actually rotate the ultrasound probe around these points. So how to propose a mechanism? And one of the things is that we do not want any motor inside the incubator because the motor makes noise. And remember, we don't want to disturb the baby as the baby is sleeping. So this is an additional requirement. So now how to propose a mechanism that can perform this very specific motion? So we come up with a specific idea that combines two pantographic linkage in series. So the idea is that you have one pantographic linkage that's mainly focused on the proximal remote center of motion that basically displays the tip of the ultrasound probe. And at the end of this pantographic linkage, you have another pantographic linkage that generates the distal remote center of motion that take care of the rotation of the ultrasound probe. So the entire mechanism is almost decoupled because the proximal pantograph linkage manage exclusively the linear motion of the probe, while the distal pantographic linkage manage mainly the rotation of the probe. So with this concept, we have 6 degrees of freedom that are required. We have one proximal remote center of motion on the access panel and another distal remote center of motion on the front panel of the patient, the baby. So as you can see, this mechanism looks quite complex. You have many linkage interacting together. But if we carefully study the kinematic of that mechanism, it's actually possible to approximate, not even approximate, to modelize the kinematic of this complex mechanism with a very simple one, with a serial mechanism with 1, 2, 3 linkage. So because we have a very simple kinematic, a very simple linkage to simulate the kinematic of that mechanism, we can rely for the resolution of the kinematic model on geometric method. So you can see that the equations are very simple. Now for the angular kinematic, we need to use rotation matrix, basically, except for the third joint, because the third joint, based on the mechanism, the third joint does not affect the rotation of the mechanism. So again, this is a little more complex, but it's still very accessible. We use one rotation matrix calculated with the angle we want to use to position the probe, and another rotation matrix calculated using the joints, the rotation at each joint. And by this process, we can identify the forward kinematic model, the angular forward kinematic model. For the inverse kinematic model, we use pretty much the same method. However, we need to isolate the three last angle that manage the rotation of the probe. The angle 1 and 2 are actually calculated through the linear kinematic model because the mechanism is almost decoupled. But the method is almost the same. So we can then identify the joint variable for the angular inverse kinematic model. So the kinematic model is very simple because we can simulate the kinematic of this complex mechanism with a very simple one. After that, we design our mechanism linkage. We design our prototype. So this is a picture of the prototype, and we use this cage basically to, because we don't have an incubator, but we use this cage to simulate the position of the incubator. So the mechanism is really above it, and this part of the linkage goes inside the incubator. And because we have a specific transmission system for the linkage, all the motor are located outside of the incubator. And what also makes the mechanism safer is that based on the physical interaction between the linkage, if we have a power failure, if the linkage, the horizontal linkage fall by mechanical interaction, this linkage will be lifted. So this is our first prototype. And then we come up with another prototype where you can see the mechanical architecture is different, but it actually generates the same kinematic. So this is our second prototype. And now we hope that we can perform some experiments, not on real baby, but on maybe on an incubator or using some doll. So this is how we were able to address the mechanical challenge of manipulating a probe with two remote center of motion. And this is something that was never proposed before. No one ever proposed a robot for the examination of baby in incubator. So now the second illustration is bone reduction surgery. So the idea is that in some fracture, very severe fracture, the bone can be completely separated into two parts because it's attached with the tissue and the muscle. They will pull the bone in different direction. In that condition, it's impossible to heal because the bone must be physically connected so it can heal. So before the ossification, traditionally the surgeon will perform an open surgery, and this is actually a very simple one. There are even worse open surgery to physically access the bone, and will physically put the bone together. And then, because you have a physical contact, then the ossification can occur. The problem with that traditional method is that first, open surgery is something in medical we want to avoid as much as possible because you have risk of hemorrhage, you have risk of bleeding, you have infection, and you take a very long time to heal from this type of surgery. The problem with that traditional method is that since you have some physical interaction with the muscle, once you place the bone back into their original place, you always have some residual motion when you have to place the prosthesis. So this can cause misalignment. A safer method is to rely on minimally invasive surgery, meaning that instead of opening the flesh of the patient, they will use a series of rods that they will directly insert, like some screws. They will directly insert it through the skin and the flesh of the patient into the bone directly. And by manipulating those rods from outside the anatomy, you can actually manipulate the bone inside. So this means that there is less risk of bleeding and infection. The problem with this method is that since you don't see the bone inside, you need to rely on intraoperative image. Basically, you need to use X-ray, and X-ray is dangerous for people. If you take a few X-ray in your life, it's okay. But for a doctor who has to do it every day, at the end, you have a risk to have a cancer or some medical problem. So this is a problem. Now, what they can do also is to use a mechanical system to rigidly fix the bone. So that way you can solve the problem of the residual motion, because the bone is not going to go anywhere after you manipulated it, because you fix the rods physically, rigidly with a mechanism. But again, you have the problem with the hazardous intraoperative image. Now, to solve this problem, you can use actually robotic mechanism to guide the rods directly. So you don't need to be physically present to manipulate the robots to displace the bone. So not only robotic bone surgery is safer for the patient, it's also safer for the doctor, for the medical personnel. It's also more accurate, and you don't have the problem of residual motion because it's rigidly fixed with a robot. So there are several types of mechanisms that are proposed for this type of surgery. The most popular one is the Taylor spatial frame. This is an hexapod mechanism with 6 degrees of freedom. So you have a full complete motion to control the 2 bones. So one bone is attached with one platform of the robot, and the other bone fragment is attached with the other parts, the other fragments of the robot. And by moving the mechanism, you can move one fragment from another. The problem with that mechanism is that the workspace is very limited. However, when you connect rigidly the bone fragment with the mechanism, you have to ensure that the trajectory you have to do to reconnect the bone will be inside the workspace of the mechanism. If it's not inside, but you have to make sure it's inside. If it's not in that, so that means you have, as you connect the robots physically with the bone fragment, you have to evaluate, is the trajectory going to be inside the workspace of the robot? And that's quite a difficult task. So our work in this application was to propose a mechanism that has the same size in proportion with that Taylor spatial frame, but that can generate larger workspace. So then it doesn't matter how you connect it with the bone, because the workspace is so large, you don't need to worry about the trajectory being within the workspace. So previously we proposed 2 different architecture that are hybrid mechanism. So we have a tripod mechanism connected with a planar mechanism. And as you can see, the workspace of the mechanism in red is much larger than the workspace of the mechanism that they usually use in medical in blue. So you can see the workspace is much larger for both prototypes. However, the problem with this architecture is that, as you can see, you have many rods inside. So it's very interesting from a kinematic and theoretical point of view, but when we want to design a real one, the design may not be suitable for a real medical application, because if you have to put your legs inside, you have very little available space for your leg or your arm. So then we turn to another concept, which is called augmented tripod. An augmented tripod is actually a mechanism with 3 legs instead of 6, but because we add more degrees of freedom into each leg, we can still generate 6 degrees of freedom. In general, with parallel mechanism, each leg gives you 1 degree of freedom, but with this augmented tripod concept, 1 leg gives you 2 degrees of freedom. So with 3 legs, we have 6 degrees of freedom. So this is the first mechanism we work on. It's not from our own invention. It was developed by a guy named Elizad. But the study he had was limited to the numerical resolution of the kinematic model. So what we did is that and no prototype or CAD were ever proposed. So we took this concept and we complete the theoretical analysis of that mechanism. We found an analytic solution for the inverse kinematic model and also for the forward kinematic model, although it's not visible in my slides. and also the velocity model, meaning the relationship between the speed of the mechanism, the speed of the joint and the platform of the mechanism. So this is the first prototype we worked on. Then we propose a second prototype, which is a little more promising. It's the same type of mechanism. It's still an augmented tripod, but the mechanism actually give more workspace. So again, so this time, this mechanism is from our own design. So again, we studied the inverse kinematic model, the forward kinematic model, velocity model, etc. And then we study the workspace of for each mechanism. We compare it to the workspace. We compare the workspace of each mechanism to that of the hexapod that is commonly used in medical. And we compare it using the same dimension. So we basically, for two mechanisms of the same dimension, which one is going to have a larger workspace? So as you can see, for this one, the first one that was not from our own design, the workspace is a little larger. But for our new mechanism, the workspace is much larger. That means if you connect the two bone fragments to these two part of the mechanism, you don't have much concern about the trajectory being inside the workspace because the workspace is so large. So this mechanism is very promising. And then after that, we design our own prototype and we perform some simulated experiment. We buy a fragment that we cut in half with a specific cutting session. And we see how easy it is using this mechanism to put the bone, to reconnect the bone. And both mechanisms were effectively able to do it. However, for this mechanism, you can see that because we have circular slider in the design then is quite cumbersome compared to the other. The other, you can see the design is quite large. You have a lot of available space. And also what is important is that the rods, the metallic rods here, basically here, you don't really need to have this circular shape here. You don't need to have this color here. You can insert the rods directly into the bone. So the mechanism should be much lighter. So to our opinion, this mechanism is even more promising for bone reduction. We have only 3 legs instead of 6, and we have a larger workspace, and the design allows to insert the rod directly into the bone, which makes the medical process easier. So that's the end of this presentation. So as a conclusion, we could see that by addressing medical robots through mechanism, so by proposing very specific mechanism design, we can not only have a better kinematic to generate motion, but we can also make the medical intervention safer. And also we can reduce the cost because we need less legs, we need less motor, the robotic manipulator can be smaller, etc., etc. So here we could see how we can address the mechanical challenge of reaching with a mechanism, with a safe mechanism, the fontanelle of a baby inside an incubator, and how also to improve the workspace of a robot for bone reduction surgery. So this is the end of my presentation. I hope you enjoy it. So now I will be pleased to answer your question. So thank you for your attention.
Thank you, Professor Terence, for your lecture today. Is a lot of knowledge, especially for me to remind what you already touched to us in terms of the kinematics, so we can see if we want to develop some mechanism in terms of the medical application, we have to consider also the kinematics. There are 2 statements that I can notice from you speaks. The first one is robot, it can make it more safer in terms of the operation, and not only safe for the patient, also for the doctor, because more of doctor can solve, I mean the doctor fatigue problem, it can be solved also by the robotic mechanism. And then the second one, thank you for your presentation in terms of the newest research. The first one is the tele echograph that used for the newborns incubators, and then the second one, I think, is, I still remember the one, I think, is in terms of the parallel mechanism for bone reduction that I think one of your students also work in terms of it. I think is from Vietnamese.
Yes.
Yes, thank you. Actually, we have as audience also in our rooms, and they are also from the Zoom platform. I will invite 1 and 2 questions, please. If from the Zoom platform, maybe the organizer can help also. And then for the stage here, if you want to ask, please invite, say your name and give the question or something that you want to comment from the Professor Terence lecture today. Please.
Thank you very much, Dr. Wansha. My name is Dr. Iqbal. Good afternoon, Professor Torrance. I would like to address only one question actually, because we in mechanical engineering, of course, we have experience in designing some mechanism, but mostly if for mechanical, so-called for mechanical machine, engine, and also for construction purpose. But this is actually really new for me. My question is regarding the material. Since we apply this robot to human, any material consideration? Maybe some material we can use, maybe some other material is not sufficient for human. Maybe you can comment on this one, please. Thank you.
Well, actually, about the material, basically the biocompatible material to avoid infection or contamination, etc. Well, for us who design robot, it's not very difficult because this is a topic that is already very well documented. So if you collaborate with the doctors, they will tell you right away what kind of material you can use. In general, for example, the prosthesis you saw on the video, usually it's titanium, for example. And you could use titanium and metallic elements also, because one other issue is that you need to sterilize the parts that will be in contact with the patient. There is basically 2 ways to address that. There are parts of the robots that must be in contact with the patient, otherwise you can't perform any surgery. And then you have some parts that could be potentially in contact, but not necessarily. For example, the elbow of the robot, maybe it can be in contact, etc. If that's just the case, you can just use plastic cover and they will have special products to sterilize it. But if this is a part